Hello everyone. So now we will be doing past papers relating to circular motion, and I have compiled three solid past paper questions of CIE, which will be a very good representation of this topic. Now, before we get started with the questions, one thing to note down is that CIE usually like to ask circular motion questions in combination with other topics. So, for example, with gravitational potential or electric potential energy, all those other topics. So these three are also quite mixed, and they are not pure circular motion, but most of it is circular motion, and you'll never find a CA question which is fully circular motion. So we will be doing these three questions, and I hope that gives you a good enough idea of how the questions are asked and how to solve them. So let's start with the first one. This is from 2023 May June. It says that there is a steel sphere of mass 0.29 kg, and it's suspended in equilibrium from a vertical spring. So you have a sphere over here, and it's suspended by a spring. The center of the sphere is 8.5 centimeter from the top of the spring. So from here to here, it's 8.5 centimeter. And you are given the mass as well, which is 0.29 kg. Now the sphere is set in motion so that it's moving in a horizontal circle at a constant speed. So they are moving this sphere in circular motion over here. By the way, one thing is that when they say constant speed, they are talking about something called uniform circular motion. And in most of your questions, you'll be doing uniform circular motion, which is the constant speed. If it's not uniform, then it can form weird shapes. Like it might not form a complete circle, it might be an oval like this, or sometimes it can form a spiral. Basically, other stuff which is might not be completely circular. So currently, we will be focusing on uniform circular motion, and most of the questions will be uniform circular motion, right? So they say that the distance from the center of the sphere to the top of the spring is now 10.8 centimeter. So you see it was 8.5, and now it's been extended to 10.8 centimeter. Okay, so part A says that explain with reference to the forces acting on the sphere why the length of the spring in figure 2.2 is greater than in figure 2.1. Okay, one tip about CIE is that if they ask you to do something in the question, do it. So here, when they are saying with reference to the forces acting on the sphere, so to get full 3 marks over here, you will have to follow the instructions over here. Even sometimes they say you may use this and with reference to a specific thing. Now, whenever that is asked in the question, try your best to solve that question using that. So let's try doing that. So with reference to the forces acting on the sphere, which forces are there on the sphere? Why is the length greater? So the first force that is obvious over here that the sphere will be its weight, right? So there will be a weight W over here. What other force is there? Another force will be the tension in the spring over here. So because this spring over here is kind of being stretched by the ball, so there's a tension over here which goes up, right? And initially, because it's in equilibrium, this T equals to W in the first diagram. Now, when we go to the second diagram, what are the forces again? We have the weight here, we have the weight, and we have the tension. But this time, the tension is not acting vertical like this. It's acting in this slanting way over here. So the tension is actually going this way because the string is bent, right? The spring is bent this way. Now, the first thing that you can see is that this tension, because it's going like this, it actually has two components. It has the vertical component and it has the horizontal component, and this is the main tension. So the vertical component is always equal to something cos theta, and this will be T cos theta. And the horizontal one will be T sine theta. So you can actually break this tension down into the vertical part and the horizontal part, whereby the horizontal one is T sine theta and the vertical one is T cos theta. So you can see that now the weight is actually being balanced by the vertical component of this tension, right? So T cos theta equals to W. And this sine theta will actually be the unbalanced force. There's nothing cancelling this out. and the unbalanced force, if you remember, is the resultant force, which is the centripetal force. So this t sine theta is the one which will allow it to go in the circle. Okay, now back to the question, why the length of the spring is greater. So the first thing that you have to recognize is that the tension must be greater, because before the whole tension was balancing the weight. Let's say the weight is maybe 10. Okay, so the tension here must be 10, right? But now t cos theta is balancing the weight. So if this is 10, then this t cos theta is 10. Okay, that means that if the vertical component is 10, then there's also a horizontal component, right? Maybe this is 5. So the main tension over here, the hypotenuse, is much more than the initial tension over here. Okay, because this time this tension is a combination of the vertical and the horizontal components. And yeah, so what we can write over here is that t is greater. And why is it greater? Because it has two components, the vertical and horizontal components. Now it has two components, and now the weight is balanced by the vertical component of it, right? Which is t cos theta, which means that the overall tension is greater. And if the overall tension is greater, that means that the length of the spring is greater, because the more the force, the more the extension, because we know that F equals to KE. So if you have a greater force over here, the more the spring will be extended, so the length of it will also increase. Okay, the next part says that the angle between the linear axis of the spring and the vertical is 27 degrees. So this one, as you can see over here, is 27 degrees. They ask you, show that the radius r of the circle is 4.9 centimeter. And it's just a 1 mark question. In CIEs, if you see a 1 mark question, there's not much to do over here. There must be something very obvious. Okay, so if you have the angle as 27 degrees, try to look at what you're provided with. You have the angle and you have this length over here, and that's basically it. And you have the mass. That's it. You don't have much else to work with. So what you can do is you can draw a simple triangle over here. We have this part of the spring, which is 10.8 centimeter. So this is 10.8, and we have the angle with the vertical, which is 27 degrees. And the radius is this horizontal part over here. So this horizontal part is the radius of the circle, and this radius of the circle will be equal to, so if you want the horizontal part, this will be sine, right? So sine 27 equals to the radius divided by hypotenuse, which is 10.8, and you should get 4.9 centimeters when you do the calculation. Okay, so I hope that was clear. You just draw a simple triangle and you use sine to get the radius. Now show that the tension in the spring is 3.2 newtons, and this should be pretty straightforward as well, because what you can do here is that you see this equation that we have formed, which is t cos theta equals to the weight. We can use this equation to find the tension T. So this equation can be used to find T. We have theta, which is this angle, which is 27 degrees, and we have the weight of this sphere, which will be mass times gravity, and mass is 0.29, right? So we can use this to get the answer. We can write T cos theta equals to weight, and T is what we are finding. So T cos 27 equals to mass, which was 0.29 times 9.81. And when you do the calculations, you shall get 3.2. Okay. Next question says that the spring obeys Hooke's law. What's Hooke's law again? Hooke's law is force is directly proportional to extension. So whenever they say that, they basically just saying that F equals to KE. This formula is obeyed. Okay, so that's the essence of Hooke's law. They say calculate the spring constant of the spring. So you are finding K, right? So you'll have to do K equals to F over E. So K equals to F is what? This is the force in a spring, is the tension in that spring, which is 3.2. So this will be 3.2 divided by, and what's extension again? Extension is the final length minus the original length, right? So what was our final length? We have 10.8 and the original one was 8.5. So when you minus these two, that will be your extension. So 3.2 divided by 10.8 minus 8.5, and you should get the answer as 0.15. Okay, use the information in B to determine the centripetal acceleration of the sphere. So they want the centripetal acceleration of the sphere. How many formulas do we know of centripetal acceleration that we can use over here? So acceleration is equal to what? Is equal to v square over r, and acceleration is equal to r omega square. But can we use either of these equations for our question here? Let's try. Uh, do we have v and do we have r? We have the radius, which was this one that we found over here, 4.9. But do we have velocity anywhere in the question? We don't, and there is no way to even find velocity over here. So maybe that's not the one. Then we also have r omega square, but do we have omega? Omega was what? Omega was 2 pi over t, but we don't have the time period as well in this question. So both of these formulas can actually not be used to solve this question, right? Instead, we have to use another formula, which is F equals to ma. So this acceleration, which is caused by a centripetal force, is called centripetal acceleration. And do we have force? We do have force. Do we have mass? We do have mass. So that's why we use this specific equation. And the force was what? The force was 3.2 and the mass is 0.29. So it's just going to be a straightforward calculations. 3.2 divided by 0.29, and you shall get the answer as 5.0. Okay, calculate the period of the circular motion of the sphere. So this time we are finding the time period t. Again, you try to think about the formulas relating to time period t. One of them which will click is omega equals to 2 pi over time period t. Do we have omega? We don't, but can we find it? You can see in this equation over here we have omega, right? We have acceleration now and we have radius, so we can find omega. So what you can do is you can just make omega the subject here. So omega square equals to a over r, and acceleration is 5 divided by the radius, which is how much did we get there? We got 4.9. So 5 divided by 4.9. We get omega square as 1.02, and we square root this and we square root this. So here we get something around 1.01. Now when we have omega like that, we can do omega equals to 2 pi over t, and our omega will be the 1.01 equals to 2 pi divided by t, 0.62. Okay, that's it for question 1. Okay, let's go to question 2. This is from ON 2021. The first question says that what is meant by centripetal acceleration. So the main point over here is that when you have an object which moves in a circular path, right? So you have, let's say, this car, it moves in a circular path. Now what happens is that there is something which is pushing it to go in a circle, right? And that's what we said is the centripetal force, and the centripetal force always acts perpendicular to the motion. So if this one, let's say the tangential velocity is like this is v, then the centripetal force will be perpendicular to this object. So the acceleration which is caused by the centripetal force is called the centripetal acceleration. And when they keep this thing as italics, so basically they really want the meaning of centripetal. So you can just say that it moves in a circular path and it's perpendicular to the velocity. Okay, the next one, an unpowered toy car moves freely along a smooth track that is initially horizontal. The track, by the way, when they say a smooth track, it just means that there is no friction. Okay. The track contains a vertical circular loop around which the car travels. So the car goes like this, whee, and then it goes back, as shown in figure 1.1. The mass of this car is 230 grams and the diameter is 62 centimeter. So the diameter of the loop is 62 centimeter. Assume that there is no resistive forces. State what happens to the magnitude of the centripetal acceleration of the car as it moves from x to y. So when the car is over here, when it's at x, what happens to the magnitude of its centripetal acceleration as it goes from x to y? So how do we do this? Again, the first thing that you should think about is formulas. In physics, most of the questions, like I'll say even maybe 60% of these kind of questions can be solved with formulas. Okay, so let's try to find formulas for centripetal acceleration. And the obvious ones are, again, v square over r and r omega square. So if we can just find the relationship of what happens between these things, let's say between v, if the v decreases, I'm just giving an example, if the v decreases, then a decreases, or if the v increases, then a increases. So this kind of stuff is what you have to figure out over here. What happens to the acceleration? And we will know only what happens to the acceleration if we know what happens to the values in its formula, because if something here changes, the acceleration changes. Okay. Regarding this formula, we can't do much over here because we have radius and we have omega, but we don't have anything to help us with this because omega is 2 pi over time period and radius is just radius. And this omega over here cannot really be used because we don't have the time period or any hints about it in the question. Okay, so let's use the top formula, v square over r. What do we know about the velocity? That when it goes from x to y, what happens to its velocity? Does it decrease? Does it increase? What change happens? Okay, so what we can do is that try to think about the energy changes. When it's at x over here and it's going to y, it's actually increasing in GPE. Okay, this is kind of going back to Form 5, but when you go from x to y, you are gaining GPE. And when you gain some sort of energy, you must lose some sort of energy. What energy is it that you lose? That energy will be kinetic energy. So the kinetic energy decreases, okay, as you go from x to y. Even usually when you go on top, you are gaining GPE and you are losing kinetic energy. Okay, and if you lose kinetic energy, remember what's the formula for kinetic energy? Kinetic energy equals to half mv squared. So if you are losing this, that means that the velocity is also decreasing because they are proportional to each other. And if the velocity is decreasing, that means that the acceleration is also decreasing. And that's why the magnitude of the acceleration will be less. So this answer here is decreases. A lot of stuff for 1 marker. Okay, let's go to Roman 2. Explain if the car remains in contact with the track, why the centripetal acceleration of the car at y must be greater than 9.8. How do we solve this? Okay, now I'll take you back to the concept of vertical circles that we were doing in the lecture. Remember, we said something about these two positions. This, let's call it position 1, and let's call this position 2. Let me just rub this so we can get some space. Okay, let's take position 1 and position 2. In position 1, how many forces are there which are acting on this? So you have the weight which is going down, right? And we had something called the normal contact force. In the lecture, we talked about it was a string, and we talked about that we say that there's a tension T in the string which is going up. But if it's a car and it's in contact with this track over here, there's a normal contact force which opposes it. So you have N and you have W. Okay, and when the car reaches over here, then the W is still going down, and the normal contact force will also go down. So this time the normal contact force will be together with the weight. Okay, so let's write these two equations. Position number 1, we have normal contact force and we have weight. And the guy which makes it go in the circular motion will be this normal contact force, because this has to provide the force to make it go in a circular motion. Okay, because we say that circular motion is it happens when you have a perpendicular force to the velocity. So if this velocity is going this way, the acceleration must go in the center, right, in towards the center of the circle. So this n must be greater than the weight. Okay, so n minus w equals to centripetal force. For position number 2, n plus w will give you the centripetal force, because both of them are acting towards the center. Both of them are making it go towards the center, right? So this will be n plus w equals to fc. So now in the question they are saying that the centripetal acceleration at y must be greater than 9.8. So at y, this is position number 2. So let's focus on this. Why does the acceleration over here must be greater than 9.8? Now let's expand this. Okay, so n plus mg equals to ma, right? Because centripetal force is resultant force, which is ma, and a is also equal to v square over r. So I can write this as v square over r. Okay. Now, if you wanted this thing to keep on going in a circle, this equation has to be obeyed. Okay. If it's not obeyed, it doesn't go in a circle. So the minimum, uh, the smallest acceleration which has to be provided is when this normal contact force is 0. Why am I saying this? Because if you want the car to be in contact with this track over here, then only it will move in a circular motion. If this contact force is 0, it's like it's tipping over, it's falling down. It can't stay in the circular path. So we have to have a contact force which is greater than 0 to make it in contact with this track over here, or else it loses the track and it falls off. Okay, so the absolute minimum is when this is 0, and it happens that mg equals to v square over, sorry, mv square over r, mv square over r. We see that the m and the m cancel out, and gravity is 9.81. So 9.81 equals to v square over r. This is just the formula for acceleration. So the absolute minimum is when the acceleration is equal to 9.81. Okay. Now, to make it go in the circular motion, this one has to be more than this 0 over here. So there must be plus a certain value, which means that this acceleration must be more than 9.81 to make it go in the circular track. I hope that made sense. It might be a lot of content and a bit complicated, but what you have to understand is that we have different equations for position 1 and position 2. In position 2, uh, normal contact force plus the weight is the centripetal force, and if you want to make this thing go in a circle, it has to be in track with this loop over here, or else it won't go in a circle. And the absolute minimum, like right before it tips off, this one is 9.81. But if you want to keep it moving in this circle over here, it has to be more than 9.81. There has to be some sort of normal contact force which is helping it be in contact with the loop. Okay, so that's why it has to be more than 9.8. So how can we write this? Yeah, all that, and we have to condense this over here. So the first thing that you can say is that what is this 9.81? 9.81 is the gravity, right? So the weight, or let me say gravity causes acceleration of 9.8. But we also have to keep in contact with the track. If the car remains in contact with the track, uh, the car requires some contact force to be in contact with the track. Requires some contact force to be in contact with track. Hence, acceleration has to be more than 9.8. Okay, let's go to the next question. The initial speed at which the car in B moves along the track is 3.8. So initially it's moving at 3.8. Determine whether the car is in contact with the track at point Y and show your working. Okay, so what we can do over here is that let's try to find the speed at point Y to see if it's in contact or if it's not. And what will that speed help us in doing? This speed will help us to find the acceleration, because you see in Roman 2, what do they say? They say that if the car remains in contact with the track, the acceleration must be greater than 9.8. So if you want the car to remain in track, the A must be greater than 9.8. And we know that the formula for acceleration is v square over r. So this thing must be greater than 9.8. So let's try to find the v, because we have the r already. Let's see how much we get for the v, and that will allow us to know if it's more than or it's less than this. Okay, we have the initial speed. Initial speed is u, right? Now I'm taking you back to kinematics in Form 5. We have the initial speed as 3.8, so this will be over here, u equals to 3.8, and we want to find v here, which is at y. How do you find this? One of the formulas for velocity was v square equals to u square plus 2as, right? U square is this 3.8 square plus 2 times acceleration here will be the gravity, which is 9.81, and the displacement will be from x until y. And remember, this is displacement, not the distance. Displacement is a straight line distance from x to y. So this will be the diameter of the circle. And the diameter is 62 centimeters over here. So we can use these values to get our velocity at point y. So let's do that. So v square equals to 3.8 square minus 2 times 9.81 times the displacement, which was 62 over 100. And you shall get the final answer for v as 1.5. So let's try this now. So 1.5 square divided by the radius, and how much was the radius? The radius was, if this is 62, then the radius will be 31, right? So this will be 31 divided by 100. I'm doing divided by 100 to convert it into meters. Okay, and you get around 7.11. That means that 7.11 is not greater than 9.8, and hence it will not be in the circular track, so it will actually fall off. So the car is not in contact. Okay, so that's your final answer. It's not in contact. Okay, let's go to the last question. Suggest with a reason, but without calculation, whether your conclusion in C will be different for a car of mass 460 grams. So the mass here has been almost doubled. Yeah, it has been doubled, moving with the same initial speed. So they're saying that will your conclusion be different or not? And how did we find our answer in C? We found it using acceleration, right? Can you see mass being used anywhere in this formula? We have never used mass anywhere, and so you can just see that mass is not part of the equation of acceleration, and hence it does not affect the result. Okay, so because we never use mass in any of our calculations, it won't matter if the mass is double or it's half or whatever. The answer will not change. Okay, the one which matters is the velocity, and they say that it's the same one, so the answer will remain the same as well. Okay, let's go to the last question of this paper. So this is from ON21 as well. With reference to velocity and acceleration, describe uniform circular motion. Okay, so I hope you're familiar with these kind of definition questions by now. Whenever they say uniform circular motion, first of all, in circular motion, they're always looking for perpendicular stuff in their definition. Okay, so when you have an object moving, they'll always want you to understand that if this object is moving with this velocity like this, there's always a perpendicular acceleration to this velocity over here, which is making it go in a circular motion, right? So that's the first part. And another part is uniform. When they say uniform, they just want you to understand that it's constant, okay? Because you might not have a constant velocity, you might have a different velocity. So with reference to velocity and acceleration, so that's what we can write. We can write that velocity and the acceleration are perpendicular to each other, and also they are constants. So we have defined the meaning of circular motion, and we have also defined what is uniform. Okay, let's go to the next one. Two cars are moving around a horizontal circular track. One car follows path X, so this is path X over here, and another one follows path Y, which is this part over here. The radius of path X is 318 meters, so this is 318. Path Y is parallel to and 27 meters outside path X. Both cars have mass of 790 kg. The maximum lateral friction force F that the cars can experience without sliding is the same for both cars. Okay, the maximum speed at which the car on X can move around the track without sliding is 94. So there's a car on path X over here somewhere. Let's say the car is somewhere over here. Okay, so they're saying that the maximum speed at which it can move without sliding is 94 meters per second. So again, we have 94 over here, maybe going this way, so be 94 meters per second. Again, to make it not slide, it has to go in a circular motion. For circular motion, you have to have a perpendicular acceleration over here. Okay, now calculate the force. So we are finding the centripetal force. Centripetal force is equal to mv square over r. Okay, and by the way, just one note, what here provides the centripetal force? It's actually the friction force, which is giving the centripetal force. So friction force provides the centripetal force. Okay, and it's actually always better to write what provides the centripetal force. So you should write over here that friction force provides the centripetal force. I'm just writing in shortcuts, but yeah. Okay, so let's do the calculations now. So the mass was how much was the mass? The mass was 790 kilograms. 790, and we have our speed as 94 square divided by the radius, and the radius of the path X is 318 meters. Okay, and you should get your answer as 22,000 newtons. Right, let's go to the next one. Both cars move around the track. Each car has the maximum speed at which it can move without sliding. Okay. Complete table 1.1 by placing one tick in each row to indicate how the quantities indicated for the car on Y compare with that on X. So we have to differentiate between the car in Y and the car in X. And you can see the main difference is the radius of these two things, right? Okay, so let's try to differentiate one by one. We start with centripetal acceleration. How is it different in Y than it is in X? Okay, so yeah, so the first thing will be to identify formulas for centripetal acceleration. The obvious ones which come to mind are v square over r and also r omega square. Obviously, you can see that in Y there is a greater radius. But how about the velocity? The velocity, now the thing is, they haven't given you anything about the velocity. They haven't said that it's the same one in Y than it is in X. They just say that each car has the maximum speed at which it can move without sliding. So both of them are in their maximum speed, but they are not saying that which one is more and which one is less. So actually, you can't use this for a fair comparison. So we can't use this formula. And in fact, we can't even use this formula because they haven't said anything about the period time. So what we are left with is one more formula for acceleration, which is F equals to ma. Okay, whereby the centripetal force equals to mass times acceleration, but this will be the centripetal acceleration. So this is equal to force divided by the mass. Now you can see that the mass of both of these cars is the same. Okay, so both of the cars have the same mass. They say here both cars have the same mass of 790 kg, and the friction force is also the same for both cars. So they have the same friction force and they have the same mass, which means that the acceleration will remain constant. Okay, it will be the same for both of them. So here the answer will actually be y is the same as x. Okay, let's go to the maximum speed. Now again, the first thing is formulas. So try to identify formulas for this. We can just see one of them right here. A equals to v square over r, and we know that acceleration is the same for both of them. Okay, how about the speed v? What changes it in r? Radius is more in y than in x, so y has a greater radius than in x, which means that for this to be constant, this has to be more as well. So they kind of cancel out to make this constant. Okay, so the velocity in y will have to be more than the velocity in x. So we can see here that y is greater than x. Okay, this will be this one. And how about the time taken for one lap of the track? When they say one lap, this is the period time. Okay, so in fact, what we will do here is we will use this formula this time. So a equals to r omega square, and omega is equal to 2 pi divided by the period time. So a will be equal to r times 2 pi divided by period time square. So let's make t the subject in this equation to know what's going to happen to the period time. So this will be a equals to r times 4 pi squared divided by t squared, and we get a t squared equals to 4 pi square r, and t squared equals to 4 pi square r divided by a. So remember, a is constant, pi is constant, and the radius for y is more. So that means that t will also increase. So we can say that the time taken for y will also be greater than x. Right, that's it. Thank you for watching. I hope you get a good understanding of circular motion and how it works. And I'm sure if you keep on solving more questions like this, I'll also leave the worksheets. You should be good to go for circular motion. Most of the questions, as I said, are interlinked with other questions, but completing these will give you a very good and solid foundation in circular motion. Okay, have a nice day, guys. See you.